Yeah, so happy New Year to everyone. I hope you had a great break. I hope you got to take some well-needed rest from, especially from all the social media and all the stresses of our everyday lives. So yeah, I'm really excited to be teaching here. It's actually the first time I'm teaching here at Caltech, and so I hope you saw what the course is about a bit online in the description. But for this lecture, I really want to make sure that any questions, any queries you have about the course, we try to resolve this. So we'll start with some logistics about the course, what the structures are. They're fairly standard, but I thought I'll go through that. And then we'll do more like a warm-up, material that I already hope you've done in other courses, but at least the most important required ones, I'll just give an overview. And from the next class onwards, we'll do the actual material for this class. So nothing new, just the same things you've heard everywhere. Okay, so I've thought a lot about this course because, doing this for the first time here, I've taught different machine learning courses before, but there I was a lot more constrained because, it was at a certain level, at a certain kind of topic, right? But here it's all across Caltech, and that's the nature of Caltech, that I get different backgrounds. So, and each of these topics I'm going to cover could make more than one course, right? There's so much material there. So I won't be able to do the depth as much as I would like, but at the same time, I can't be covering everything possible. So there will be the balance. And for me, think of the aim of this course is not to understand everything perfectly, right? I don't think even I can't claim I would be successful in doing that, but more as a way to, there is so many papers now in machine learning. If you're new to this field, I suggest not to subscribe to anything on archive. Don't subscribe to archive, updates, because every day you will get hundreds of papers coming into your, and you won't be able to go through them, right? So the main purpose is to try to sift through so much of material and try to pick some nuggets, pick some what I think are important papers, important new results in the last few years. And at the same time, first introduce the classical theory, right? What was known for a long time, and what were some of the new advances that came about, and what is still open. So that's what I'll try to structure the course as, And so because the classical theory itself would take a long time, so I won't be able to cover a lot of it. But I will mostly introduce the concepts and maybe give you what the main results are and some proof ideas. And I expect you to go back and look into the details of the proofs in your own time, because we won't be, at least maybe the important ones I'll derive, but not all of them. But at the same time, there will be what I hope a lot of critical discussions in this course on, is this theory even relevant, right? Should we even bother about it? Okay, it's beautiful back, but is this going to impact AI in the coming decade, right? So I want to ask those difficult questions as well, because especially if you go look online, you look at kind of a lot of empirical results that are coming up and all kinds of marketing hype, right? You think that theory has no relevance, right? Or maybe you don't because you're at Caltech, but many others seem to have that viewpoint. And so I think it's important for us, I consider myself a theoretician, and I think many of you here may be comfortable with that label, for you to also critically think what's relevant and what's really missing in our current theories, right? And at the same time, the systems that are being run are extremely complex, right? You can't directly analyze them, right? The way they are run, there is no way. But what is that right middle ground of simplifications where you could potentially have some theory, but at the same time, it's much more relevant to practice. So we'll try to ask those difficult questions. Sometimes there are no answers, but I want you to think in that way. That's what I hope you will get out of this class, right? So that's the main one. The main intent is really to try to pick some what I think are interesting material in these different areas and get the main ideas from these papers. So there is no recommended textbook. At the end of this lecture, I have some, like I think the textbook, Kevin Murphy's textbook on machine learning I like, but again, it's not compulsory. Right? So this is something you can look up for the introductions and the concepts. But mainly we will do a lot of papers, and some of them very recent papers through the course. Any quick questions here, or even detailed questions? So that's the overview, and that's the overall course. It's a lot. It's like as I said, each one. So each lecture is going to be densely packed, right? So there is. I debated a lot, and I came up with this because I think each of the topic is really important if you want to do research in machine learning, or you want to apply machine learning in a serious way even into other areas. And we, so it's going to be tightly packed, and so I really, there'll be, in that sense, it'll be a lot of work in this course. So we'll start with optimization, and that's why there is this recitation tomorrow to get you, kind of have a recap of convex optimization, because we'll just jump to non-convex analysis in the course. Because I think many of you have done convex, but I guess only a few of you would have thought about the non-convex cases, right? But now with neural networks, that's really what it's about, right? We really want to understand non-convex optimization, but I mean, if you just say non-convex, that's everything except convex, right? So that's not conveying anything. So what additional assumptions can we make, and what kind of weaker guarantees can we provide, and how is it relevant to machine learning, right? So we'll ask those questions. And when I say competitive problems, it really means more of the flavor of min-max or other kinds of, it's not just single agent, there are multiple agents. And now with generative adversarial networks and other machine learning problems, this will be important as well. But this is going to be much harder, right, to give any kind of guarantees. But there's a lot of interesting work over there. In fact, very recent, just over the last year. So we'll go through some of that. So spectral methods, that was my bread and butter for many years. It still is in many ways. So, with linear algebra, it's essentially all of machine learning, what underlies is linear algebra, right? So with matrix methods, what I really mean is what you can do with just low-rank matrices or other kind of structured matrix assumptions, how you can make machine learning very tractable. And then we'll go to tensors, so that's extending matrices to more dimensions. Even simple concepts like rank become a lot more involved. There are many notions of tensor rank. The optimization landscape becomes much more complicated, and in general, all these are NP-hard problems, but in many cases, you can even analyze and provide guarantees. So how we're going to exploit these tensors, whether to look at multi-dimensional data or higher order moments, right, and how we can use them in different latent variable estimation problems. So we'll see that. So then comes the midterm, which will be the presentation of project proposals. So I put down 2 lecture sessions here. We have to, given the size of the class, and I think we said usually 2 participants for each team, right? Like the team size is 2. We'll have to work out the logistics and how much time you can get. So it'll be like a proposal, and also like you submit a proposal as well. So that's that. We took the break, and then we'll get into representation theory, like how, what are neural networks representing, right? Like how can you talk about a finite-sized neural network, and what class of functions can it represent? What is the capacity of these networks? So we'll do some classical analysis of this, but also so much is still unknown for these deep neural networks, right? So most of it is for shallow networks, we have good results, but beyond that, many open questions, but I'll also try to give you like an idea of what's the recent progress here. And then generalization, there is like one lecture with all the classical results. So this will be, if you've seen it, it's straightforward, but I want to make sure everybody has their copy. And then this lecture 10, even, I don't know, we'll have to see, because there's so much of there's so much talk about generalization being a mystery in deep networks. So this will be more of those lectures where I'll try to review the material. I'll also give some of my personal thoughts, but a lot more open questions, right? Like, why is it so difficult in deep networks? So robustness, we'll see, is also important. So there is the classical robust estimation, but then now also robustness in the context of neural networks. How to enforce that is a very difficult problem. But there's a lot of interesting progress in the last few years. So then we'll kind of switch kind of ground, right? Like until these were all like supervised learning, then we'll do generative models, 2 lectures for that. And then after that, it's more, I would say these are really like the, in a way, cutting edge, right? Like there is almost very little theory available, even in the classical sense. But these are highly important for as machine learning takes off in humans. I mean, usually we don't have much data, and you have to collect your data in an active way, right? Like you can't just collect the data all passively in the beginning and then do machine learning. You want to collect it as you are doing the learning. You want to figure out what are strategic data points, how should you collect them. And so it's very interesting, but there's, I would say, a lot of open problems there in theory and also practice, if you're interested. So domain adaptation, we see a lot of this, right? So the most common uses of neural networks is where they take pre-trained ImageNet and then transfer it to some new data set, right? So that's the most common way practitioners use machine learning. And so, but we hardly understand how this transfer happens. I mean, which layer should you transfer? What should you do? I mean, there is no theory, right? So it's very hacky right now. But can we say, like, what is the theory here available and what are open problems? Like, how can we go from one domain on which it's trained to a different domain on which you're testing, right? What assumptions can you make that would make it tractable, and when is it relevant? So we'll ask those questions. So then lecture 16, so far I think this is the last one I put. I mean, lifelong learning is a very general term, and it's still a very, I would say, like, not many people are looking into it because this is so difficult, right? So lifelong learning could be, in the most general form, your environment is changing, you still have to keep learning, right? There's no notion of stationarity, right? There's always some new knowledge to learn. How do you keep learning that? And how do you keep adapting? I mean, it's related to reinforcement learning, but still some experts say there are ways to distinguish. So we'll, again, debate more about how we can formulate the problems here. So at this point, let's say. So I've left these 2 lectures still to be determined, mainly to see how the class goes. Sometimes, I'm compressing a lot, so I may end up using that for what topics I think there is a lot of interest in the class. And so that's why, I want you to leave comments on Piazza, so that I can get to know as the class is proceeding. If you feel like it's too fast or too slow, let me know. I hope, it's hard in a diverse class, but I hope we can, have everybody go through the class. And then there's the final presentation. Any questions? Yeah, so again, I mean, if you're, many of the terms, you don't have a background, you may not have caught all of them, and that's okay, we'll go through them, but I think at least I wanted to give an overview to make sure you got an idea. Okay, great, so with this, now actually I want to give some warm up and give, at least some 101 courses, right, on both probability, statistics, and machine learning. So for some of you, this may be, introductory, but I want to make sure everybody is on the same page. So how many of you here have done like a measure theory class? Yeah. So no, I think actually measure theory is an easier way to understand probability, right? So yes, it can get more abstract and going through a whole course can be very involved, but I at least want to give the basic formulation so that what measure theory really helps you think about probabilities in terms of sets, right? Like you're measuring sets, and so thinking about events in terms of sets makes it a lot easier. Like all the properties, all the different theorems in probability come out more naturally. So we'll go through this a bit now, and then we can jump to some statistics. So if I write here, can everybody see? Those are the corners. Somewhat, so I'll try to write only in the middle, so hopefully that will. Because I don't want to put everything in the slides. I think that will, I feel like, make the class more passive. So I prefer whiteboards or blackboards. I think it will much more interactive. So does anyone remember how to describe a probability space? What are the main ingredients? Okay, there's the sigma algebra, but even before the sigma algebra, what's the? There's something else. We should bring markers next time. Okay, so what are the ingredients? Does anyone remember? What's the first thing you want to think about? Sample space, right? So it's usually this omega notation. So there's the sample space, then there is the sigma algebra, and then what's the probability function. So for specifying any probability space, you need to think about all the three. Right? So this is the sample space. Sigma algebra. And then the probability. So what you're really doing is using the probability function to measure the sets in the sigma algebra. Right? So that's the idea of probability. So now, what are the constraints on the sigma algebra? What properties should it satisfy? So first of all, what's sigma algebra? Right? So it consists of some subsets of the sample space, right? So everything is only, the sample space is like kind of the union of all the possible events that you want to measure, right? So sigma algebra will be subsets of the sample space. But then it can't be any arbitrary collection of subsets, right? You need further constraints. So why is that? So the idea is you want to ensure that if there is a subset in the sigma algebra, then its complement also is in the sigma algebra. Which kind of makes sense. You want to make sure the complementary event should also be there. Right? So you cannot discard that. And the other one is like the union. So if you have there's some collection of subsets that are present in the sigma algebra, its union should also be there in the sigma algebra. Right? It can't be any just arbitrary collection. But this is natural, right? You definitely want the complementarity and you want the union. So that's all you need, right? So it could be any arbitrary collection you're thinking about, but you should satisfy this problem. Okay, and so that's on the sigma algebra, and then for the probability function, does anyone remember the axioms? What are the basic axioms of probability? Can you speak up?
Countable adjective.
Additive?
Yeah, countable additive.
What is countably additive?
So,
what is countably additive? Can you?
I think if A1 to AN is disjoint, then the probability of them is the sum of the.
Yes. So that's kind of like, the union is defined, so we know union will be there. So we're now saying that's actually the third axiom, right? But we'll first go with that. That's okay. That's the most. So if these are disjoint, you want to make sure that it can just happen for countable kind of set of five. I mean, the very first one is, of course, it should be between 0 and 1. Actually, this is what distinguishes probability from general measure theory, right? So here you're using this constraint, and then and of course, the other basic axiom is like the probability of the sigma, the sample space is 1. So this is all you need, right? So from everything else you can, everything else is built upon just these basic axioms. So what I find very powerful from this formulation is, now when you think about it as sets, like all the union bound, the Borel-Cantelli lemma, there's the Bayes theorem, everything just flows naturally by thinking of it as sets, right? Like that. So I'll give some examples of that, but I will post notes that has all the details, so we will not be able to cover all of them. There are some really obvious ones. There's, of course, if a set A is contained in set B, right, then the probability of A should be less than 1, right? Because, it's like if you're measuring sets, then this is like a natural way to think about this. Right? So, and then the union bound also comes naturally from here. So we saw if it's disjoint, the probability is additive, right? But if it's not disjoint, it is just a bound. So it's just an upper bound. And so how do you see this? The idea is if you have now, let's say this is the full sample space, and we have two sets. Right, so if there is some overlap here, right, that would be the, so it would be the probability of A1, A2, and then it's minus the intersection. Right, so it's like the inclusion and the exclusion property. So for two sets, you can write it this way. Right, so you're just decomposing the union into both set A, set B, but then you have to subtract the intersection because you're counting it twice. And so, right, so that's how you have the union bound. Yeah. So again, interrupt me because so if anybody's seeing some of this for the first time, it takes longer. But don't worry, I want to make sure everybody can see and understand this. So these are. So I want to go into Borel-Cantelli lemmas. That's when you have like a countable set of events. There is the notion of infinitely often and all but finite number of times. So these are things when you have a countable set of events, you can ask about these properties, but they also kind of arise as an extension of these bounds. So the other, I guess, important notion is conditioning. Can everybody see if I write here? Yeah? On the corner there? No, not really?
Not really,
Yeah. So how can you think of conditioning in terms of sets? I want you to speak up, otherwise
Intersection of sets?
I'll write down, so probability of, let's say, an event in 1. Right, so now I have like sets here. So what is the interpretation of what this conditioning means in terms of the sets? Right, so this proves it not. Sorry, the sample space.
The area of the intersection divided by the area of that zone too.
Yeah, so that's the formula, right? But how can you see it in the figure? Can you interpret that base rule in the figure? Yeah.
If you think of D2 as a sample space.
Exactly. Right, so you're now changing your sample space, right? Now earlier it was this whole sample space, but you condition on E2, that means the sample space is only this, right? So it's only the E2 set. You're ignoring everything else. And so that's why you need to rescale this intersection event, right? Because you want to like now say, what is the, how big is this intersection event when compared to probability of E2, because that's my new sample space, right? So it's like once you think of it in terms of sets, it's really obvious, right? So whereas I feel like otherwise it's a formula, right, with not the same kind of meaning. And yeah, so that's how you get the conditioning. You can also do the, I think it's called the total probability theorem. So if you have a sample space, you take a partition. So you can take any partition of sets. Let's say this partitions are EI. And so now I'm taking a partition, and then now I want to measure any new set. So I want to take the probability of some set here, let me call it set B. I can write it and decompose it in terms of the probabilities under each of the events. Right? So if it's a partition, then that way I can measure the whole. So essentially what I can decompose the probability of set B, right? I can look at each of the parts here, like how much is it under event 1, how much is it under event 2, and so on. Right? So I'm looking at the conditional of, B, under each event EI, right? And then I'm scaling up with the probability of that EI, and then I'm taking this. So if these, can everybody see this? So if all these sets EIs form a partition, you can decompose the probability of any set in terms of the conditional events, right, EI. And from, again, the set theory, this is really kind of coming out immediately, right? Because you're measuring what the probability is under each of the events EI and just scaling up with this. Right? So, and that's, of course, the same as like probability of B intersecting with each of these sets. So this is kind of like, some of the basic identities in probability, but I mean, what I really, if you haven't done measure theory before, the purpose here is to start rethinking of probability in terms of sets. I think that's can be much more useful, especially if you have like somewhat strange events and things where it's not obvious how they're interacting. I think that's mostly what I wanted to talk in terms of basic probability, but any questions here? Yeah, so we'll now go to some bounds, like concentration bounds. So again, there are entire courses on this. Joel Trop has a great course on random matrix theory and other, there are also other courses. So but I think some of the important ones I'll just go through to again, mostly, as a refresher. So what is the main idea, right? So if you have a complicated probability function, you cannot really, you may not even have it in a closed form, and even if you do, it's too complicated, you can't be evaluating it everywhere. So instead, you would like bounds, right? And the question is, can we write these bounds in terms of just simple moments or simple properties of the distribution, right? So even if you don't know everything about the distribution, there's some simple information we can extract, and that's why it's a bound. So the most basic bound is called the Markov Inequality. And this is for non-negative random variables. So let's say h of x is h is non-negative. So let me write it. So x is some random variable such that you can take a function of x such that it's non-negative everywhere. Right? So now if I want to ask what is the probability that h of x exceeds some value a. So again, for this to be meaningful, a is also non-negative, actually strictly positive. Right? So these bounds are typically very useful because you want to really be, what you're interested is this variable exceeding certain value. Right? So we'll see in a lot of statistics and a lot of analysis, all you care about it is exceeding certain value. So these are called deviations, and this is the simplest form. Right? So you're looking at how much, what's the tail here for this positive random variable. So this is, let's say, the probability density function, and so you're only looking at the tail beyond. Right, so this is going to be very useful in a lot of the analysis, and what this bound says is, this is a very simple bound because it only depends on the mean of the variable. Right, so it says that it's the ratio of the mean of the variable to the value a you're asking. And because this is only the mean of the variable, this is also pretty loose bound, right? Because there could be many distributions with the same mean, and the bound is the same for all of them, right? So this is using the simplest information, just the first order information about the random variable and giving a bound. So with this Markov's inequality, actually you can build many other bounds. So there is the Chebyshev bound. So what you do with Chebyshev is, it uses the mean and the variance of x, but doing so, it's only taking a special case of the function of x, right? What it's doing is looking at how x deviates from its mean. Right, so if you substitute the function to be just the deviation of x from its mean, then this, and then you take some a to be some epsilon, right? So this is the standard actually squared, right? So because what it's saying is, how much a variable x is deviating from its mean value depends, the bound of it depends on the variance, right? So if naturally you have a large variance, it's going to deviate more from the mean, and it has and the other way. So again, it's only using first two moments and nothing else about the distribution. So usually it tends to be a loose bound, but many times it may be enough. So that's the Chebyshev bound. And then the, actually a very good bound is the Chernoff bound. So this will involve the complete information about the random variable. So, but any questions so far? notation not clear? Was that clear? So yeah, so so there are so many concentration bounds and inequalities. But what I said is just to remember the Markov's inequality, right? So almost every other inequality can be derived from that. So that's the starting point. So the Chernoff. So what you're doing with Chernoff now is you're taking the function. So again, you need it to be a non-negative function. This time you're exponentiating the x. So you're looking at, let's say, e to the lambda x, right? So this is a non-negative function, you can always do this. And then the tail bound, you're using again your exponential integrals. Right, so if you do this substitution, you have probability of, because this is monotonic, this is the same as x exceeding certain value, right? And this is now less than or equal to right, e to the, sorry, so this is, so you just write this. And right, so what is this here? Just the e to the lambda x. So what is the expectation of e to the lambda x? What is this function called? So this is the moment generating function. So does the moment generating function contain all the information about the distribution? Right? It does. Again, there's some, I think, technical conditions, but for those where this exists, it encodes all the information. Right? So the idea is, in this case, this is the tightest bound because you're, compared to the other ones, compared to Chebyshev, because you're using complete information about the distribution. Right? But it also means, in general, this is hard to evaluate. You have like moment generating function in closed form for some simple distribution. You take exponential, Gaussian, all those distributions, you can evaluate it, but not for any kind of complicated distributions. Right? So in general, you wouldn't be using the actual moment generating function, but what you will do is actually assume some kind of dominance with a well-known distribution. So the most common phenomenon are, these are sub-Gaussian and sub-exponential distributions. So essentially what you assume is the moment generating function is dominated by some Gaussian distribution. Those variables are called sub-Gaussian random variables. If the moment generating function can be dominated with an exponential distribution, then it's called a sub-exponential. Right? So these are again classes of distributions, but there what you can do is get the bounds to be very simple, right? Because for Gaussian and exponential you can evaluate them in closed form. So that's the most common way to deal with tail bounds. So again, so far I've only dealt scalars. If you do like matrices, that's when it gets more complicated, right? So most of the time what people do is not look at the, so if x is a vector, then they do like a norm bound, like what is the bound on the norm of x, and so you can like ask about these kind of bounds on spectral norm or other kind of norms on the random vector or even random matrix. So you can build up theories for even higher order objects. So there's a whole set of literature, and Joel Kopp's course deals with random matrix theory. Right? So there's the Bernstein's bound, and there's a whole class of bounds there. But all that starts with this. Right? So the Chernoff bound is really the starting point of everything. But it's too complicated just the way it is, because that's the full generating function. So you try to upper bound it with simpler forms. Any questions here? So that's what I intended to do with these. Oh yeah, and then just go back and also remember the law, law of large numbers, central limit theorem. I won't write them down here, right? So all these asymptotics, it's good to kind of just go back and brush that up. So the idea will be, sometimes with if you're looking at IID samples and we are looking at the empirical loss and so many of those quantities that will involve averages. So the law of large numbers and these Chernoff bounds and some of this will be a good building block there. Good, so that was with probability. So we'll do a very quick statistics 101. So that will, again, I cannot do all of this for sure. So it'll be the very quick. But all these are concepts that I hope you'll go back and brush up because we'll be using them quite throughout the course. So what's the basics, right? So when we are thinking of a model-based estimation problem, what we typically have is some unknown parameter. Let's call this theta. And then there's some observation model, right? So this is the model which says it's some probability distribution, right? So or probability density function. So I'm drawing my observation y, right, given theta. So the probability distribution function is a function of the unknown parameter, right? So that's my observation. Right, so I'm observing y, and then from that I need to estimate what this parameter is, right? So that's my estimate. Right, so this is the basic estimation, right? So have some unknown parameter, and then based on the observations, you would like to estimate this. So this is the parameter estimation problem, but sometimes it can be the function estimation problem, right? They're estimating a whole function, and so that's a next step. But the very basic is the parameter estimation problem. And its frequentist to theta, you assume no distribution on it, it's some arbitrary parameter. It's Bayesian if you assume there's a prior distribution, right? So frequentist is when theta is just fixed, right? There's no assumption of a random distribution of it. Bayesian is when theta has some prior. Let's say pi of theta is the prior. And in a fully Bayesian method, what you do is not just take the point estimate, but actually the posterior, right? Because what you really care about is what is the probability of theta given all my observations, right? So what is this distribution of this unknown parameter given everything I've observed so far, right? So it's not only giving you a point estimate of this unknown parameter, but it's actually giving you the full distribution. So you even know the uncertainty of what values theta can take, right? You know the probabilities. So that's the fully Bayesian method. So there is indeed, of course, a long-standing debate between frequentists and Bayesian researchers, so I won't get into that. I think both methods have merit, right? I mean, ultimately, if we had infinite computation, we would be doing Bayesian, right? Because we don't just want a point estimate, we really want all the uncertainties, right? I really need to know with what probability can I expect this value to, this unknown parameter to be taking different values, right? But many times in high dimensions, there's no way we can get to the full posterior, and so there is a whole line of research on how to approximate it, how to do like middle ground between frequentist and Bayesian. So that's a whole lines of research. But this is the basic distinction, right? So there is the frequentist method where theta is fixed, and then there is the Bayesian where you assume a distribution of theta. Any questions here? So this is the basic, but we'll introduce sufficient statistics. So how many of you have seen sufficient statistics or remember the definition? Okay. We really need more statistics courses here. So, so does anyone recall what sufficient statistic is for those who've seen it? Yeah.
It's a quantity that completely characterizes the distribution.
Yeah, so what would be like a necessary and sufficient condition to ensure that?
So if we're trying to estimate the minimum of some distribution, like a uniform from A to B, but we don't know A or B, and we're given a whole bunch of samples. In this case, the sufficient statistic would be the smallest of those samples. That would be the sufficient statistic for A.
Right. It's kind of like the lower bound of the distribution. You're saying all you really care about is the minimum of the samples, right? And that's intuitive because none of the others matter, right? Because you're asking what is the lower end of the support, and for that, the minimum value should be the sufficient estimator. But more generally, what the definition is, right? Like how do you decide if something is a sufficient statistic? So let's say T of y I claim is a sufficient statistic of for that estimation problem I talked about, right? For estimating theta. So what I want to look for is this conditional distribution, right? So once I know the value of T of y, how does the probability distribution of y depend on that, right? So what is this conditional distribution? And so if this is the sufficient statistic, can this be a function of theta? No, right? So this cannot be a function of theta if you need it to be a sufficient statistic. Right? That's because if, we are saying all you need to know is T of y. If you know this function of y, that's all you need. Right? That's what we're calling it a sufficient statistic. So then the conditional distribution should have no dependence on theta, right? Because that means that's additional information it will get. So this is the technical definition for sufficient statistics. And so there's also the Neumann-Fisher theorem. So this is actually really a foundation in statistics. What this is saying is, if you have the probability distribution, sorry, this was the likelihood function, right? So this is like the observation model. So this is looking at the PDF of y given theta, right? I should be able to write it in terms of a sufficient statistic. So what we will do is we'll factorize it into two parts. So there'll be one part that depends on the sufficient statistic, and it's also a function of theta, right? So it will also depend on theta. But the other part, which will depend on y, will have nothing to do with theta. So you can see, like, these two should be both definitions for sufficient statistic, right? They're equivalent. Because what this is saying is, if T of y is a sufficient statistic, it should incorporate all the dependence on theta, right? So you should be able to write one part of the function that depends on theta, and then the rest of it, each of y has no dependence on theta. Right? So in this case, both g and h are non-negative, which you don't want any negative functions for a PDF. Are the two definitions clear? I mean, this is a theorem, but really these two are equivalent. Right, so you could have a very complex PDF here in the model, but if the dependence on theta is simple, the rest of it doesn't matter. Right, I can abstract all that out, like I don't need to worry about this. Any questions here? Because I know most of you have not seen this before, so I want to make sure. I think this is a very important concept, and we don't use it much in machine learning, but I think there is a lot of thinks it could help us understand better if we use the notion of sufficiency.
Can we just give some more words to say T and T of Y? So like T is a function from this set to that set.
Oh yeah, so T is a function of Y, right? So T is from R to, I mean, it depends on Y. I'm assuming a scalar random variable. In this case, T is just R to R.
Okay. And we would call T the, T is the sufficient statistic, or is T of Y the?
T of Y.
Okay.
Because statistic is usually a function of your observations. Right? So let's take some examples. So if you have like IID data, let's say you have x1 through xn, these are all IID from some distribution. Right. And let's say what I don't know is the mean of the distribution. Let me just make it frequentist, right? So when I write this semicolon, that means it's frequentist, I'm not conditional. So I want to come up with an estimator for the mean of IID random variables. What do you think a sufficient statistic is? So I'm telling you a whole bunch of random draws from a distribution, and I want to estimate its mean. What's a sufficient statistic? The empirical mean, right? So, I mean, of course, all the data itself is sufficient, right? So trivially, what you begin with is already a sufficient statistic. But the idea is you want to make this as low dimensional as possible. And this is called the minimum sufficient because you can't do better than this, right? So the empirical mean in this case will turn out to be the sufficient statistic. So I encourage you to go and check with these results, but intuitively as well, it's kind of clear, right? So, but this really, for complicated estimation problems, right, it makes it, I think, more obvious what is sufficiency. Yeah.
And you said it's the minimum sufficient statistic. You mean you can't do better dimensionally?
Yes.
Or you can?
So there's also like other notions, I won't go into it here. It's called the information bottleneck, where people have been relaxing this notion. So they don't assume a strict sufficiency, right? So it's no longer strictly a sufficient statistic, but then they could further reduce the dimension, but it's no longer sufficient. So they're trying to trade off sufficiency with dimension. And you'll see many deep learning papers with this notion. So that's the connection. I know if there is time in a later lecture, we can revisit this. But I want to make sure that everybody here is aware of sufficient statistics. Right? This is very, I think, critical. Even if you don't explicitly use this notion, I think, underlies it.
So what's the intuitive reason for G and H in the theorem? Like, what is their interpretation?
Yeah, so the interpretation is you can write all the dependence on theta, right? So in this PDF, there are some parts that only depend on the observation y, and then there are other parts that depend on theta, right?
Okay, but neither of those are the statistic you're trying to get from the data.
What do you mean by statistic? Statistic is the function you're...
Exactly. So like H is not the statistic that you're pulling out of the observation.
No, but T of Y will be, right? Okay. So what we are saying is, you can pre-process all your data and just give me T of Y, and then from then on I can just use that to do my estimation. I don't need to worry anything about the raw data. Right? And this actually, could also help you be private, right? Like if you're only giving me the mean and not the actual samples, then it's also private, right? So there could be other benefits by summarizing this into a sufficient statistic and not give me all the raw data. So that's the main idea, that you're summarizing this and still maintaining the relevance for your estimation problem. You're not losing any information while reducing the dimension. and processing the data. Right, so that's the strict notion, and that's what a lot of classical theory does. But the more modern notion is called information bottleneck, where you relax this. You say it may not completely preserve the information, maybe I'll lose some, but on the other hand, I can summarize it better, right? And there have been a lot of interesting advances that try to analyze the information bottleneck. Any quick questions here? Or I guess we are almost out of time. So. No? Yeah, so what I'll do is I'll post some of the lectures from statistics I did in a previous course. So we will, at least the plan of the course right now, we won't be going into it, but I think statistics is something that's useful irrespective of all the other things we'll see, right? So try to look into that.